Good morning. Today we're going to be looking at what it takes to actually convert numbers from decimal to binary, hexadecimal, and vice versa. So let's go ahead and take a look at the basic structure here. We've been using decimal numbers for most of our lives with the idea of using 0 to 9 as our base case. Everything starts off at 0, goes up to 9, and then when we reach the next column, aka the tens column, we then have 10. So we have 0 to 9 in the ones column, a 10 is the next column, so we have right here this lovely imaginary line. And what we have on this is the idea that we are using powers to actually organize our information. And so if we take a look at this, we have the 10 to the 0th power right here. The 0th power always is the numbers 0 to 9, because it's the maximum possible number that will fit inside there. And we go to this next one, and so this is the 10 to the 1s column, aka the tens column. And so in the 10 to the 1s, in this case, we have 1 times 10 to the 1 and 0 times 10 to the 0, or a total of 10. If we're to change this right here, and make this be, instead of 10, have it be 70. As 70, we have 7 times 10 to the 1. 70 plus 0 times 10 to the 0, or 0 times 1, which is 0. So a total of 70 right here. The same basic approach works for all of the number systems, except that instead of having it 0 to 9, like we have for 10, the different number systems all start at 0 and go up to, but not including the number that we're looking at. So if we're looking at for binary, so we have decimal up here. We do binary, we have the idea of our 2 to the 0th power, and our 2 to the 1st power, and our 2 to the 2nd power. And because we're doing binary, we only have the numbers of 0 and 1. Just like we have in our 10th, we have 0 up to 9. So up to, but not including the power we're using as our base. And so 2 to the 0th power is still 1, just like 10 to the 0th power is 1. So 1 times 2 to the 0 is still 1. In the case of 10 in binary, like you'll see in some of those shirts making fun of people who don't know binary, we have the idea of 1 times 2 to the 1 plus 0 times 2 to the 1, aka there are 2 types of people. So we have that number right here. So we have 10 in binary is the same as 2 in decimal. And we'll take a look at how we can convert that here in a moment. Our last one we're going to be looking at for our framework right here is the idea of hexadecimal. And our hexadecimal idea is the idea of using a base 16 system. Hexadecimal is the base 16 system, aka base 16. We have base 2, base 10. Base 16 goes up to, but not including 16. But because we only have a single digit to represent that, we use the F going from A to F, so we can count those spots, 10, 9, 10, 11, 12, 13, 14, 15. But we only have one character to represent it, so we use the capital A through F to represent those numbers on that. So that same framework right here. What we're going to do is we're going to go ahead and take a look at how to convert them now. So let's go ahead and look over here. And to look at the idea of converting from a number to another type, we have a couple different things we can do. When we're going from decimal into binary, we have a couple different options. There's the idea of subtracting powers of 2 method, where we identify the powers of 2 that exist inside the decimal number, subtract them out, and keep on going down. And that's really good if you happen to have your powers of 2 memorized and know the order that they go in. Unfortunately, sometimes little things like that can trip people up, and so that's why I'm not going to encourage that for this one, but I'll show you a quick sample. In the case of the idea of 18, we have our number right here, 18 in base 2, or sorry, in base 10. It's a decimal number. And so our 18 number, we're going to convert this to binary. So we want to figure out the biggest power of 2 that fits in that. Oh, 16. So we'd subtract 16 out, and that leaves us with 2. Oh, biggest power of 2 that fits in there is 2. Okay, great. So we know that we have a 16 and a 2, but how do we put that together? We have to actually know those powers in order so we can put it together properly. Now, I happen to know that if we go ahead like this, we have the idea of 0 times 2 to the 1 plus 1 times 2 to 0 times 2 to the 0 plus 1 times 2 to the 1, which is 2, plus no 4s, plus no 8s, plus a 16. Here's our number for 18 in binary. And I happen to know that right there, but we have a better way to do that. We have the idea of a reverse division method. And so we're going to use reverse division to do this on a regular basis. Let's see how we can do that right now. So we have our powers of 2 subtraction method we just saw. Reverse division, we're going to go ahead and use a little bit different setup. So I'm going to go over here. I'm going to take the number 18. Clearly, just like what we have. We're going to use the division symbol. We're going to use it upside down because we're going in reverse. And this is going to help us put this number together in the right order. Now, the way we do this with the reverse division is that we keep on dividing by number 2 until we get down to the value of 0, because 2 goes into 1 0 times with 1 left over. And we'll have our final value put together with that. So let's go ahead and do that right here. So we have 2 goes into 18, and 2 goes into 18 9 times. And there is 0 left over, so we write a 0 over here just to the right. We have 2 going into 9. Again, we repeat that division process over and over again. 2 goes into 9 a total of 4 times. with a remainder of 1 because 2 times 4 is 8, giving us that remainder of 1 that we put over here. Again, put the remainder over to the right. 0 if there is no remainder, a 1 if there is remainder. 2 goes into 4 a total of 2 times. 2 goes into that with 0 remainder. 2 goes into 2 a total of 1 time with 0 remainder because it's an even division. Again, finally 2 goes into 1 0 times. However, there's 1 remainder because 2 does not fit into 1. And so we have that remainder of 1 right here. And then again, to continue that process of reverse division, we build our answer from the bottom going up to the top for our left-right answer. So we have the 1 0 0 1 0 in our number in binary order ready for us to go. So as you can see, this reverse division process where I divide by 2 over and over and over until I get to 1, which leaves us with a value of 0 with 1 left over. And I build that answer from the bottom up, 1 0 0 1 0, to build my answer right here. And this number works for any division of converting from binary to from converting from decimal to binary. If I go ahead and add another number to this, and the idea of, say, for example, I want to do 318. So I make that number a little bit bigger. The same process will apply. So we'll erase the results right here. And so 2 goes into 318 a total of 159 times. So 2 goes into 318 159 times with 0 left over. Okay, looks the same. 2 goes in 159 times, so we have 75 plus 4, so 79, with 1 left over. Again, because we have the idea that we have that leftover information. So 2 goes into 79. It doesn't go into it 40 times because there's not enough to get that, so we have 39 times. And it goes into 39 times with 1 left over. 2 goes into 39, a total of 19 times. 2 goes into 39 19 times with 1 left over. Again, that process came in over. And then 2 goes into 19 a total of 9 times with 1 left over. 2 goes into 9 a total of 4 times with 1 left over. 2 goes into 4 a total of 2 times with none left over. 2 goes into 2 a total of 1 time with none left over. 2 goes into 2 a total of, or 1 a total of 0 times with 1 left over. And again, building from the reverse back up, we can go ahead and also convert this lovely binary sequence right here into a hexadecimal sequence. It's really actually quite easy. All we have to do is we have to take that same binary sequence, in this case the 1 0 0 1 1 1 1. So 1 0 0 1 1 1 1 1 0. So we have 1 2 3 4 5 6 7 8 9. 1 2 3 4 5 6 7 8 9. Perfect. Okay. So we have our lovely binary sequence right here, transcribed as a regular binary sequence number. And so that number right here is the same equivalent for what we have of 318 using decimal. As you can see, when we're converting from decimal to binary, our number sequences drastically grow because of the fact we have a change in power. We're going from a 10-base system to only 2-base system, so our numbers are going to get drastically bigger. In the case of this, we have the idea of a 256 plus some information, all those powers of 2 that get involved with that. And that's how this number is put together in the binary versus the idea of having 3 times 10 to the 2 plus 1 times 10 to the 10 plus 8 times 10 to the 0. We have to have our 1 times 2 to the 5th, blah, 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 blah. So we're going to go ahead and grab that over. And so to do this, to convert to hex, all we have to do is we have to take this and put it in chunks of 4. So we start over here on the right-hand side and 1, 2, 3, 4, imaginary line. 1, 2, 3, 4, imaginary line. Oh no, that's not an example of 4. So what we have to do, we prepend it with zeros. Because zeros at the beginning of the number don't have negative impact on that at all. So we just go ahead and add some of that for there. So this number right here is just going to be 1 because it's just adding that value of 1. So that has 1 right there. No big deal. This number right here, we have 0 plus 0 plus 2 plus 1. So we have 3. Okay. And in this number, we have 8 plus 4 plus 2. So 8 plus 4 is 12, plus 2 is 14. But 14 won't fit in this one spot thing. So again, like we have over here, over in hexadecimal, we have the idea that we start off at 0 through F. So that goes to 0 to 9, and then A up to F. A is 10, 11 is B, 12 is C, 13 is D, 14 is E. So we go ahead and place that within E. And so our number right here is 13E inside hex for the same number that we have as this huge big sequence here in purple, in binary, as well as our lovely 318 right here. Now, this shows that we have the ability to really compact numbers. If 318 gets shrunk down only to 3 digits right here, but we can see because this number is going to get up until powers of 256, there's 1 256 in this. However, there's 3 times 10 to the 100. So this is going to get bigger much slower than this does, and even way slower than we have our binary sequence growing. And so this is why hexadecimal becomes very powerful, because we can have the idea of having a much bigger representation, say for example a memory address, in a much shorter amount of space like we have right here. And so we use the idea of having that compressed information by using the 13E for that sequence. So that's where we're going to leave off for now. Thanks and have a good day.